It's all walled off from blood pressure. So you have to slice into the area to release fluids to bring the swelling down enough that the tissues will begin to get a blood supply again, live again, and be able to receive antibiotics. Now, there's another trick we can use when the inflammation area is a little smaller. You can attach leeches, medicinal leeches, which will attach to the tissue, rasp a hole in it, suck the fluids out enough that the swelling goes down, blood supply to the area is revived, the tissues can live, antibiotics can now flood in. So believe it or not, we're redoing
Thank
leeches.
you for asking that.
Leeches are big again for localized inflammations like that and for skin grafting and various grafts. I think we'll get a look at those guys later on. All right, so now what we're going to do is look at some representative connective tissues, appreciating that when you have an immune response, whether it be good or bad, it's because something's happening in the connective tissue in your body. So the first of the, I didn't mention fibrogen. I'm sorry, I'm jumping ahead of myself. I didn't mention the fibers in connective tissue. We talked about the matrix, which is filled with water and proteins. And we talked about the cells of various types, including immune cells and resident cells, cysts and blasts that actually make the matrix. But we didn't talk about the fibers. All connective tissues have lots of fibers of varying types, depending on whether the connective tissue needs to be hard or resilient or bouncy. So one of the most common types are thick ropes of material called collagen. Long, thick bands of protein ropes. Collagen fibers, extremely strong. They have what we call a lot of tensile strength, which means that when you pull on them, they don't give. They're like a rope of steel. So any connective tissue that needs to be really strong, like bone or tendon or ligament, is going to have a lot of collagen fibers. When you want to pull on a tendon, you don't want it to stretch. You want it to be strong. So it's almost all collagen fibers, tendon and ligament. However, if you have a connective tissue that you want to have a lot of bounce or give, like the connective tissue in your ear, okay, it has very little collagen fiber. Gosh, if you had only collagen fibers in your ear and you slept on your ear with the flap closed down, when you woke up, your ear would be broken and hanging down like a basset hound, right? It's got to be able to bounce back, right? Your nose, lots of areas of your body have to have connective tissue with bounce and resiliency. So they have less collagen and more of what we call elastic fibers. They're long, they're thin, they're often curly, and they have a lot of rebound, a lot of ability to bounce. They're not strong, but they are elastic. And then finally, some connective tissues that have to act as a support, like a scaffolding, have a lot of reticular fibers. These are thick, dark, branch fibers that really just hold things together. For example, your liver, any soft gland of your body, is permeated with a connective tissue that has a lot of reticular fibers to hold the tissue together. If you remove the reticular fibers from your liver, it would just flow in a puddle. So reticular fibers act as a scaffolding or support. All right, now we're ready to look at the kinds of connective tissues that you're going to be seeing in the laboratory. And I'm only going to ask you in lecture to identify each of these probably by what they do, or a bit of pathology is relevant. So the first of these is a loose connective tissue called areolar connective tissue. You see it, it looks like goo. So if you've ever lifted the skin off an uncooked piece of chicken, okay? You know, you can lift the skin right off chicken, but it's stickiness underneath. That's not nothing. That's areolar tissue. It's a delicate, loose glue that kind of holds things together. The internal organs in your body rest next to each other without rubbing because they're bathed in little wrappings of areolar tissue. And you might find areolar tissue underneath the lowest layers of your skin, loose, open, and airy. Let me see if I have another example of it. So lots of watery matrix with collagen and elastic fibers, but again, the texture is open and airy and wet. So it acts as a kind of delicate glue to hold things in close proximity. It also holds and stores a lot of water. You always need water, right? So in particular, underneath your skin, you will find between your skin and your muscle probably, will be a little zone of areolar tissue that holds a lot of water and fluids. And sometimes when your circulatory system isn't working properly or you have a lot of inflammation, the areolar tissue will fill with water. And you have seen this. This is edema. You've all had swelling for one reason or another. Gosh, you know, if you just stand too long, your feet swell. And they swell because the blood delivery back to the heart slows down a little and blood pools in your tissues, water leaks out and fills all these tissue spaces that are not empty. They contain areolar tissue. So this woman has severe edema. You can see the handprint that's left. We call this pitting edema. Very often happens with people who have heart disease and aren't rapidly and smoothly moving their blood around. All right, how about adipose tissue? Or fat. Now this connective tissue's job is to store spare calories till times of need. And there's no doubt that the storage deposits are nice cushions and pads and supports, but mainly adipose is meant as a storage system. So it stores a lot of fat, a lot of adipose under your skin. But if you open up the body cavity, any little empty spot, there'll be a little ball of fat in there. Just wherever the body can find a little empty spot, it's going to store a lot of fat. Your whole digestive tract is just ornamented with fat balls like ornaments on a Christmas tree. It's actually very disgusting to look at. But there it is. Now this is a connective tissue that's mostly cells. There's very little matrix or fiber. I mean, I can't see it in here somewhere. But all these big white things are adipocytes or fat cells. Now since their job is to store fat inside each cell, most of the cell is transparent. It's a big ball of liquid oil. And the actual contents of the cell, the nucleus and the cytoplasm, are pressed to the inside of the cell. Now I'm going to show you some pictures that might clarify that a little bit better. So here are enlarged pictures of fat cells. These are just a little more. Each fat cell will look transparent. The nucleus and cytoplasm here, here, here. And then here's an even larger picture of individual fat cells. So you can see the big oil droplet that dominates the body of the cell, and then all the rest of the cellular contents pressed to the inside of the cell. So a fat cell that's full is going to look more like this, rounded, with the cell components pressed to the inside of the cell membrane. If you lost a lot of weight or starved, the fat would be mobilized out of the cells, and the cells would shrivel up until they looked like wrinkled prunes. And then the cytoplasm contents would spread out a little bit more. So when you look at these under the microscope, this is what you're going to see. On a lower power, it's going to look like a net. Okay? Doesn't it look like a net? So what is this? I don't know what that is. So it's going to look just like a fish net. That's adipose tissue. And then when you get into a higher power, you'll actually be able to see the hollow fat cells. You won't know what these are, but these are blood vessels. These are all adipocytes here. These adipocytes are a little wrinkly because they've given up some of